Hello, everyone, and welcome to the afternoon session. Our first speaker is going to be Nick Gurski, and he's going to talk about generality, repetition, and difference in two-category theory. Nick, if you are ready, you can share your screen and take the stage.
All right. There we go. Welcome, everybody. No, I have to be able to operate the slides. There we go. I want to start by saying thanks to everybody that's involved in any way in this conference, but particularly the organizers who have dealt with trying to get this going for a very long time and have done a fantastic job. But I also want to say thanks to them for the specific wording of the invitation that they sent me, which was now about 18 months ago. And they included these requests for this talk. They requested that I talk about some sort of two-category kinds of stuff, but with some historical context, some general motivation, and something to interest the wider community. So I've had a long time to think about what I wanted to talk about. And while doing that, I sort of recalled two little stories that I'd like to share before we get going. The first was a question from a colleague who fundamentally just asked, what's the difference between two-category theory and one-category theory? And I think at the time, I said something about how some of my work was about balancing different kinds of universal properties. So in a two-category, you can express universal properties at varying strengths, and playing these off against one another is an interesting problem that leads to a lot of good mathematics. And after that, he asked me, is that it? Not in like a sort of, not in as mean a way as I think it came out. And at some level, you know, the difference is two cells. Two categories have two cells, and one categories don't have two cells. But that's significantly underselling what's going on while you're trying to do some two-category theory, and focuses, I think, too much on the obvious difference between the objects that you're studying. So the second was a question from a student who asked, why should I study n categories? As a person that's done lots of three-dimensional category theory, I've gotten asked a version of this question a lot of times, and it's a hard question to answer, and I think that's because I don't think it's phrased in a sort of particularly inviting fashion. So the invitation got me thinking about these two things, and that led to a sort of journey of thinking about how I wanted to talk about my research. And instead I would, if I could go back to this student, I think a better question is more, why do you study two categories or three categories or something like that? And then I would have quite gladly shared a lot of things that I personally find exciting while doing the mathematics that I do. And so that's kind of the philosophy underpinning the rest of this talk. Now, the title of the talk is manifestly stolen from the French philosopher Gilles Deleuze, and he sort of gives interpretations for the three words in the title. And I would like to tell you a kind of vast simplification of what I mean and why they're relevant to the kind of question like, why do you study two categories or three categories? So the first is this concept of difference that he has. And so difference is pretty much what you expect. It's how things are different. But the important aspect is that Deleuze doesn't see this as a sort of measure of deficiency, but rather a kind of affirmation of the things that make any given object of study special and worth attention. So he sees this as a kind of primary way that you think about a thing is how it's different from other things. So the second concept is generality. And this one is mostly here in order to contrast with the third, which is repetition. And so generality, this is my one-line attempt at explaining his notion of generality, the quality of different instances having the same features. So things to focus on here are exactly the kinds of things that we encounter routinely in mathematics or science or something, where there's a law that just says this is how this kind of thing behaves. That's an instance of generality. And so the final one is repetition, and this is sort of the dual to generality. And so this is when unique instances of the same event, and it's important that these are sort of events, have different features. And one is supposed to think of exactly the kinds of things like repetition in art or poetry, where the same word or the same symbol gathers different meaning to itself depending on the surrounding context. So he's got these three sort of ideas about how we could think about things like art. Now, what is this supposed to tell you about two-category theory? It's supposed to say something, because I think a lot of the time when we look at theorems, what we're looking at is an instance of this notion of generality. This is always true. You know, every number that satisfies this property also satisfies this property. But in actuality, sort of the human practice of two-category theory, I think often is more like this notion of repetition. And let me give you an example of precisely the kind of thing I mean. So here are two theorems. Theorem one, cat, the category of categories and functors, is a monoidal model category. And theorem two, cat, the category of two categories and two functors, is a monoidal model category. And I think when you look at these theorems, they say fundamentally the same thing. We often think of what's going on, or we treat the theorem as a sort of thing in action. And so the interesting part is the conclusion that is a monoidal model category, and then we're plugging in different things that can be monoidal model categories. So if all you're interested in is kind of using the theory of monoidal model categories to do something, then these are functionally the same. But if you look at the proof of theorem 2 is much more interesting, because, you know, the thing I've elided here is what the monoidal structure is. And the monoidal structure in the second of these theorems is much more interesting than just the Cartesian product. The Cartesian product does not give a monoidal model category. And this sort of uncovering of these differences is actually the thing that we do when we're trying to prove a theorem or study some kind of object. So these concepts are going to sort of guide the topics that I want to discuss today. So here's an outline of the talk. So the first thing I want to do is I want to discuss what I've labeled the expansive joy of two categories, which I think could just as easily, from a different perspective, be labeled the expansive despair of two categories. I'll get to an explanation of what I mean by that in just a moment. And then parts 2 and 3 are going to be discussions of some research projects that I'm involved in where we get to see this kind of thing I'm going to point out in part 1 in action. So let's talk about 2 categories. I wanted to start at the very beginning and build things up, because how we kind of get to our situation, like what we understand as the objects of study in 2 category theory, does influence, you know, what you do and how you do it. So what's a 2 category? The short definition, of course, is that a 2 category is a category enriched in the monoidal category of categories and the Cartesian product. So this means that a 2 category has, like any enriched category, it has some objects, and we draw those, you know, as sort of dots or vertices as usual. And then between those, it's got Hom categories, and a category itself has objects and morphisms. So the objects of the Hom categories are the arrows or the 1 cells, and we draw those in the usual way that we would draw an arrow between objects in a category. And then the morphisms of that Hom category, well, they go from one object to another, which is to say from a 1 cell to another 1 cell with the same source and target. And so they get this picture that looks a lot like what we would think of as like a natural transformation kind of picture. And then, of course, that's the paradigmatic example of a 2 category. So this is the most basic definition, and now we have really a lot of choices as to where we go from here. So I'm going to start, and we will not diverge from the kind of next choice that you have, which is what are the morphisms between 2 categories. And in this talk, there are always going to be 2 functors. So 2 functors are the enriched notion of functor, if we're thinking of a 2 category as an enriched category. And they're also the most obvious and straightforward notion of kind of algebra preserving map that you might have. They map cells in the source 2 category to cells in the target 2 category, and they preserve everything that you could possibly preserve. So they preserve the dimension of the cells. So 0 cells map to 0 cells, 1 to 1, 2 to 2. They preserve all the composition laws, which come from either the enriched structure horizontally, or if you're talking about 2 cells vertically, that's the composition in the Hom category. And they also preserve the identities. So all of our morphisms for this talk are going to be 2 functors. But of course, we have higher dimensional cells than just the morphisms. And I'm going to discuss 3 different ways that you could get to these higher dimensional cells between 2 functors. So the first, and from the perspective that I've presented so far, the most obvious is that of enriched transformations. If the objects are enriched categories and the morphisms are enriched functors, then the next thing up ought to be enriched transformations. So here's a definition outline that an enriched transformation consists of, for each object, a component. So for each object in the source, a component for that object in the target. And there's one axiom that decodes to ordinary naturality in the case that we're talking about sets. So what does that mean here? Here, that means we get 2 natural transformations. So if I've got 2 functors, f and g, then for every object x of the common source of f and g, you get a component 1 cell, alpha x, and it goes from fx to gx, just as it would for a natural transformation. And this single axiom then breaks down into 2 parts. So the first part is what happens for the one cells. And fundamentally, this is because the axiom for an enriched transformation says that two different functors are equal, and they have to be equal if they're equal on both objects and morphisms. So on objects, this is what happens, and we get just an ordinary looking naturality square, and this is the axiom for one cells. And then for two cells, you get this equality of pasting diagrams, and I've left these boxes empty. Those boxes are just instances of the ordinary sort of one-dimensional aspect of naturality. And I prefer to just go ahead and leave them there in general. You can economize this definition somewhat by requiring the reader to remember that certain composites of one cells are equal, but for purposes later, we want to keep these naturality squares plainly visible. So these are enriched transformations. This is one kind of two cell you might get. So what about a different kind of two cell? And this comes from the perspective of two monad theory. And what we can do here is, instead of thinking about enriched category theory, we can think of two categories as being the algebras for the sort of free two category construction, which starts with a category enriched graph. This is like taking the free category on a graph, except this graph has some extra structure, namely it's got 0 cells, 1 cells, and 2 cells, and then the 2 cells can be composed vertically. There's no horizontal composition. That's what the monad, or in this case, actually, the two monad is going to build in. And anytime you have a two monad, you get a two category of the strict algebras, say the strict algebra maps and the algebra two cells. The strict algebras are the two categories. We designed this two monad to do that. The strict algebra maps are going to be the two functors. Once again, that's essentially my construction. And what are the algebra two cells? So the algebra two cells are called icons. And so an icon from F to G exists only if F and G satisfy this additional requirement that they're the same map on objects. So we need that F of X is equal to G of X for every object X of their common source. And if that's the case, then an icon consists of components, now a single component for every one cell. That's the little f here. And the component alpha f goes essentially from ff to gf. And that only makes sense because fx and gx are the same and fy and gy are the same. If those were not the same, then we would have to fill in the sides, which of course is exactly what's going to happen later. So these are the icons. And the third approach that I think is fruitful to think about is the fact that 2cat itself is a Cartesian closed category. So you can just equip it with the Cartesian product and then go and produce an internal HOM in much the same way that you would do for ordinary categories. So this internal HOM, if I've got two categories C and D, the internal HOM C comma D has objects, which are the two functors. It has one cells, which are the two natural transformations, and it has two cells, which are the modifications. So this is how we're starting to see some three-dimensional structure. But the one cells that we get here in the HOM2 category are the same as the enriched transformations that we found before. Now, we've gotten a sort of start by using three different ways to come up with some viable two cells to study. And I want to talk about how we can generalize some of those. And one way to think about this is we can try to take our notion of enriched transformation and we can try to take these icons, which are the algebra 2 cells, and we can try to stick them together. And we can say, what common notion of 2 cell encompasses both of these? And these are Oplax transformations. And so an Oplax transformation has components for objects, just like an enriched transformation does, but then it has components for 1 cells, these are these alpha Fs, just like an icon does. But now the 2 cell parts, so these components alpha F, have to live in this little square, whereas with an icon we had equal signs vertically. So this is one way you can get Oplax transformations. And of course, once you've seen this, it's easy to just reverse the direction and come up with lax transformations as well. And the name icon comes from this acronym, Identity Component Oplax Natural Transformations, because in the case that your Oplax transformation has all of its alpha x and alpha y's, the identities from fx to gx, so in other words, those are now the same object, you recover exactly icons. There's a little asterisk here because this is only true sort of in the literal sense of the word exactly when we're dealing with 2 categories and 2 functors. If you move to a more general context, then maybe it's safe to say these are still the same, but we have to be a little bit more careful about how that works. So we talked about the fact that 2cat is a Cartesian closed category, and the internal HOM produces 2 functors, 2 natural transformations and modifications, but it's got 2cat has some other interesting monoidal structures, which are called Gray tensor products, variously named after John Gray. So how do these work? These work by the following observation. In the Cartesian product of a pair of 2 categories, we have the following equalities amongst 1 cells, where this is true in the Cartesian product of categories as well, that all of these 1 cells would just be equal. And so the idea behind the various Gray tensor products is that we should relax this equality and replace it with something else. So these all get notated C tensor D, but there are really 3 different ones. And what you do is you take the equation in the first line, you remove that F comma G in the middle. It just doesn't exist anymore. You only have F comma 1 composed with 1 comma G, or 1 comma G composed with F comma 1. And then the various Gray tensor products put a 2 cell, either going from left to right, from right to left, or an invertible 2 cell between them. And these are all part of some closed structures, and the internal HOMs that you get out of these will give you lax or oplax or pseudonatural transformations as the 1 cells in that structure. So these are some different ways to get these various kinds of 2 cells that arise once you start exploring the different closed monoidal structures on the category of 2 categories and 2 functors. So this gives us this kind of picture, where we have lots of different kinds of 2 cells. We've got the 2 natural transformations in the top middle. We've got the icons sort of on the top left. I've written icons. That would be identity component lax natural transformations. I don't think anybody has ever written this in a paper, at least to my knowledge, before, but there's clearly a lax version if there's an oplax version. We've got the pseudo-natural transformations kind of in the middle. 2 natural include into pseudo-natural, and pseudo-natural include into the lax and oplax. And so this is what this word expansive is supposed to mean. You have a lot of choices when you are working with 2 categories about what kind of 2 cells you want to think about. And that's one of the the specific things that I really enjoy about the subject is you get this feeling of kind of really crafting something yourself, because you have a lot of tools to choose from, and you have to pick the right one. And there are some general strategies for how you might want to pick the right one. So if your two categories are sort of the multi-object monoidal category, I don't really like this phraseology, but people sometimes use it, or thinking of a two categories, a generalized monoidal category, then icons are exactly a generalization of monoidal transformation. So that's an indication that maybe icons are the two cell for you. If on the other hand, you want to do a lot of kind of ordinary enriched category theory, then you should pick a two cell that arises from enriched two category theory. And that's usually two natural transformation, but it could very well be pseudo-natural transformations. What I think is even more satisfying than eventually nailing down the correct two cell to use is actually when you get to mix these kinds of things together in a single piece of work. And that's really what I'm going to tell you about in the sort of second half of this talk. Some projects of mine where I got to experience a really interesting mixing of different kinds of structures in two category theory, which, in the process of discovering those, I found extraordinarily satisfying. So the first of those is this topic of group completion and symmetric monoidal two categories. All right, so this is going to be, as it says, a very brief history of algebraic K-theory, part one. So at the beginning of algebraic K-theory, there were some ad hoc definitions of some groups defined by various authors. The first of these is K0, defined by Grothendieck, which is the free abelian group on isomorphism classes of bundles if you want to do things geometrically, or just modules if you want to work purely algebraically, modulo a relation coming from short exact sequences. So you view the middle term in your short exact sequence as the direct sum or the sum in this abelian group. Then there's K1, which by Bass and Shanuel, and the definition given there was, as I've written, GLR mod ER. So here R is a ring, GLR is the infinite general linear group. So you just embed GLNR into GLN plus 1R by placing a 1 and making your matrix bigger, and then you take the colimit of those. So that's GLR. And then ER is the subgroup generated by the elementary matrix operations. And I'm not going to get into the motivation for why this was a good K1, but it came from thinking about some of the geometric constructions using bundles. And finally, K2 was first described by Milner as the kernel of some map from what's called the Steinberg group to this E of R, and then later shown by Matsumoto if you were dealing with a field that you could do the multiplicative group of the field tensored with itself. This is a tensor product just over the integers, mod this subgroup. And these groups were related by what looked to be the start of long exact sequences, like you'd expect if you were just thinking about like the homology groups of spaces. And so one of the goals was to get a general notion of these groups Kn that would satisfy this kind of long exact sequence and allow you to do calculations as are traditionally done in algebraic topology. And Quillen was the first one to come along and kind of package all these all these K groups together into kind of one succinct but maybe difficult formula. So let me tell you what that was. Quillen gave two constructions, and they both give these algebraic K-theory groups as the homotopy groups of a space. So the first definition is that Kn of R is the nth homotopy group of this space BGLR plus, and this is only true for n greater than 0 because this BGLR plus space is path connected. So it's pi 0, which is supposed to maybe be K0, is clearly not correct, and you have to just do K0 by hand. So what is BGLR plus? So I already told you what GLR was. It's the infinite general linear group over R. B is the classifying space. And then this plus construction is something slightly mysterious that as one consequence builds in that GLR mod ER part that we saw in K1. But it does a lot more on the higher homotopy groups as well. And then his second definition was that Kn of R is pi n plus 1 of BQP. And this is a homotopy group, and this is not a path-connected space. So I need to tell you the base point, and the base point is 0. So here, R is a ring. P is the category of finitely generated projective R modules. Q is a new category that Quillen constructs from, say, any exact category. And then B is, once again, take the classifying space. And Quillen proves that these give you the answers that you want. Now, in defining these and going through this theory, there's a kind of intermediate construction, which is this S inverse S construction. So this starts with a nice symmetric monoidal category S. Previously, we were thinking about a ring R, and so in that case, the symmetric monoidal category in question is going to be something like R modules or finitely generated projective R modules. And so what Quillen does is construct a new category S inverse S, and you should think that this is like universally adding inverses of objects to S, except not in a purely algebraic sense, but in a kind of homotopical sense. And this S inverse S construction compares nicely to both BGLR plus and BQP. So this is how you prove that these two constructions of algebraic K-theory, which you can separately show give the correct things in sort of K1 and K2, and once you correct the first definition, K0 as well. But what do they do in higher dimensions? And this S inverse S is the thing that kind of stands in the middle of them and tells you that they give you the same higher algebraic K groups. Okay. So one of the projects that I've been involved in for a long time is thinking about generalizing a lot of these constructions, moving from symmetric monoidal categories to spectra in algebraic topology, generalizing those to two categories. So along with Niles Johnson and Helica Sorno, we've studied an S inverse S construction for two categories. And so here's not really a theorem, but this is more like you could go look up some things in a few papers and you could make these two points. So the first is that you can make an S inverse S for symmetric monoidal two categories. That one is straightforward, I think, at least in interpretation, but I'll say a bit more. And then the second is that it does the things that you want it to do. So let me talk more about both of these, not in great detail, but to give you a little bit of the idea of what happens when you study some of these things. So the first of these is you can make a definition of S inverse S. And this follows very much in the pattern of kind of more of the same, but just one dimension up. So the objects of S inverse S are pairs of objects, and you're supposed to think that the pair A comma B is supposed to represent the formal difference B minus A. And that's what happens here. The one cells in S inverse S for symmetric monoidal categories are equivalence classes of certain kinds of things. When you move up to 2 categories, you drop the equivalence class, and the thing that used to be the equivalence relation essentially becomes the 2 cell, and it's got to be subject to its own equivalence relation, which has basically the same format. So this is very much, you just do the same thing that you were doing in dimension 1, but you keep going. And this is really the most sort of naive kind of repetition that you might have in 2-category theory, where you just take a concept and there's a straightforward generalization following the same pattern. Now, the most important parts, or sort of working with this definition of S inverse S, also follows a kind of different pattern in 2-category theory. And that's using a notion of a lax comma object. And the pattern in 2-category theory is this mixing of a strict universal property with a non-strict structure. So for an oplax comma, you start with the same data that you would start with for a comma object. And now what we're putting in is the universal object up here. So this is like my lax comma object, and then a 2 cell, just like a comma object. But this is now a lax natural transformation. And so the lax comma object is the thing which comes equipped with the data in this square, and is the universal thing in the sort of ordinary strict sense. So there's an isomorphism of sets somewhere giving you this universal property. Now, part 2 of this, pointing at a number of results and calling it a theorem, is that it does all the things that you want it to do. So the first is that the kind of most important technical feature to prove is thinking about a comparison between these lax or oplax comma objects and the strict sort of thing, which would just be an ordinary pullback. This uses some 2-dimensional notions of vibration, and I've listed a bunch of people that have written some nice papers previously where they've studied aspects of this kind of construction before, or maybe in the case of Jonathan Shishe, he's sort of studied the idea that maybe this comparison is the main thing you want to do. But the idea here is that if I start with one of these cospans, and I look at the pullback, well, the pullback is a commuting square. So there's like a little secret equal sign in this square. But of course, an equal sign is an instance of a 2 cell. So maybe let me call this like pullback. And so the universal property of, say, the lax comma object or the oplax comma object is that this is equal to. So now I've got my pullback here, and I've got, say, my lax comma object here with its 2 cell, and there's a unique 2 functor from the pullback to the lax comma object that makes the whiskering of the the universal 2-cell give the equality in the pullback square. And so one of the main things you have to work with when studying some of these things is, when is this comparison map some kind of an equivalence? And it turns out that the right thing to do is to study when one of the legs of the original cospan is a fibration of some sort. So this is how you sort of do some of the technical aspects of this. But these are generalizations of what I would call some pretty standard methodologies. And to finish off all the proofs, there are a bunch of spectral sequence calculations, and those are pretty standard as well. So we make a spectral sequence. A spectral sequence usually comes from a double complex. Ours comes from a double complex. Those often come from something like a bisimplicial set. Ours also comes from a bisimplicial set. But the bisimplicial set is fundamentally, I think, a little bit different. And this was the place that we felt like we'd really uncovered something interesting. The PQ simplices of this bisimplicial set come from a 2 category, a sort of Halm 2 category using lax transformations. And those lax transformations have components which are themselves op-lax transformations. So there's a mixing here of lax and op-lax transformations that I had not encountered before. And this has to do with fundamentally like taking a simplex and cutting it in half and thinking of some as sort of the incoming half and the outgoing half, and those have to be treated differently. And one of those is lax and one of those is op-lax. When we finally wrote down this interpretation, I felt really good that when people would read this paper and we made them read the definitions of both lax and op-lax transformations, that we were going to genuinely use both of those in the same paper. That hasn't occurred for any kind of interesting reason in other work that I've done, and I quite enjoyed that discovery. I'll point out before going on to the last topic that there are some other kinds of mixing that have come up in this project. So I mentioned these constructions of Quillen, and we talked about this S inverse S, but another one was this BGLR construction. And along with Niles and Angelica, we're still thinking about the kind of 2 categorical analog of this BGLR. And there, the mixing is now something more like 2 natural transformations whose components are icons. And that's been like another source of something quite interesting. Okay, so I'm going to end with a discussion of a different project on some Tanaka reconstruction in dimension 2. So here's, once again, a very brief outline of kind of the basic problem. So you start with, this is the easiest version of Tanaka reconstruction, really. You start with a field K, a co-algebra A over that field, and from that you can make the category of finite dimensional comodules over A. And the question is, if all you remember is the forgetful functor from finite dimensional comodules over A to finite dimensional vector spaces, can you get A back? So if you've forgotten what A was, but you remember its comodules and the forgetful functor, how do you make A again? And the answer to this question is yes, you can get A back. And there's a nice co-end formula. So this is the co-end over all of the finite dimensional comodules. U is the underlying vector space. So UC is the underlying vector space of the comodule C. The star here is just the dual space in the category of finite dimensional vector spaces. And so you tensor together the dual space on C with C, and then you take the co-end over C. Now, if A is finite dimensional, the proof that that this coend gives A is just the innate lemma, and there's nothing else going on. So Tanaka reconstruction is sort of really trying to address the problem that you would run into if the innate lemma doesn't quite get you all the way there. And the second thing I want to say is if you write down this coend as a co-equalizer, then you're co-equalizing a pair of maps that go into the coproduct. And this is the coproduct over all these comodules of UC star tensor UC. That's gonna reappear in just a minute. So David Yetter and I wanted to do a kind of two-dimensional version of this. And so what do we have to change when we go from the one-dimensional version to the two-dimensional version? So the first thing is that you've got to just kind of adjust your basic definitions. In the one-dimensional version, where you might have symmetric monoidal categories, we've chosen to work with permutative gray monoids. So these are a sort of semi-strictification of the most general notion that you'd encounter, which would be symmetric monoidal bicategories, where you would work with a closed structure, a closed monoidal category. In the one-dimensional case, we have to have a closed monoidal structure on one of these gray monoids. Where you would need duals in the formula that I just gave you, well, we need a notion of duals in a gray monoid. And then you can kind of put all these things together and get compact closed structures. And so we need compact closed structures for gray monoids. A lot of these things have been studied in various guises, but one of the key decisions you have at the beginning of one of these projects dealing with structured two categories is how strict can you make your structure? Because the stricter you can make it, the easier it is to work with. And so this permutative gray monoid is a well-known semi-strictification that's kind of as strict as you can get of a symmetric monoidal bicategory. And it's a very straightforward thing to work with. But many of the rest of these have only been studied in the context of monoidal bicategories. And so there's some interesting coherence kinds of questions. You know, how strict can you make your closed structure? The very first thing that I wrote down is like a possible definition of a closed monoidal two category in this context. Definitely did not work. You know, it was too strict. And so we ended up kind of backing off of that. But I think there are a lot of interesting questions as to like how good can you make these structures? So the second thing we have to do is we have to do this kind of coend, or maybe compute it as a co-equalizer, and that's been replaced by a codescent object. And if you're thinking, you know, what's the co-equalizer that I'm generalizing? Well, it's the co-equalizer of these two one cells here. But the codescent object is sort of a two-dimensional version of this, with obviously more data in terms of one cells and objects. And it's also got some two cell isomorphisms, are the kinds that we're dealing with. So this is one of the technical aspects of how we have to generalize. Okay, so here's kind of our two-dimensional version. What do we start with? We start with a closed permutative gray monoid. So this is one of these symmetric monoidal two categories with a closed structure. And it needs a bunch of colimits because we're going to take some colimits later. We need a full sub-object of that has all duals. This is supposed to be the analog of all vector spaces in the first line and finite dimensional vector spaces in the second line. We need an enriched two category C. It's V enriched, and this is like your category of comodules. And then we need an underlying functor that goes from C to the kind of finite dimensional pieces of V. Okay, and so from this, what we do is we make a codescent diagram. And this is going to be the analog of trying to write down, this Cohen formula for reconstructing your co-module. And if you remember back to the codescent diagram, the object 1 is the sort of common target of the thing that used to be the co-equalizer. And here, that object has the same form as the formula for the ordinary Tanaka reconstruction colimit. So we've got this codescent diagram. It's a diagram in V, but not in VF. And this is, once again, exactly what happens in ordinary Tanaka reconstruction, right? You might not get a finite dimensional vector space. So here's an example theorem of what we get is that if you take the codescent object of this, you get what I'm calling a geminate comonoid. So this word geminate means sort of like doubling. And the reason is that this comonoid doesn't sort of come with the obvious structure that you'd expect. It comes with a slightly doubled version of that structure. So these are supposed to be like pseudo comonoids in a monoidal bicategory. I'm going to drop the pseudo part. But instead of one co-multiplication, you get two co-multiplications, a sort of left favored co-multiplication and a right favored. But you also get an isomorphism between them. So you haven't really done anything fundamentally different per se, but what you have done is you've expressed your algebraic structure, or co-algebraic structure, I suppose I should call it, in a kind of expanded format. And the rest of the data sort of intertwines the two co-multiplications. So I'm gonna end by showing you some pictures of what the co-associativity axiom looks like for these geminate comonoids. So here's ordinary comonoids or pseudo comonoids. The delta is the co-multiplication, so my comonoid is called C. This little backwards alpha, so alpha might be a good name for an associator if we were doing pseudo monoids or monoidal categories. We've used a backwards alpha to denote a co-associativity isomorphism. And so this is essentially the MacLane pentagon for monoidal categories, but it's the global version and backwards. So if you kind of turned everything around appropriately and then specialized to the case of categories, then you would get the ordinary pentagon for the associativity isomorphism in a monoidal category. So what do you get for these geminate comonoids? You get this. So I have to go around putting delta L's and delta R's everywhere. And I want to say focus on this square over here, just to give you an idea of the definition of this co-associativity isomorphism. So you can see the square has a delta L and then a delta R, and that's going to be isomorphic to a delta R and then a delta L. And that's this intertwining that you get. But if you look at this picture, you'll see there are clearly too many labels for one cells. And that's because I've notated that there are some secret isomorphisms in here. So for example, this one cell has two different labels. And what I really mean is the source of this is the delta L tensor 1 along the outside. But the first thing I have to do is use the isomorphism between delta L and delta R. So I'll just go ahead and. So those are all the sort of ones that are doubled. And so you can take this picture at home and kind of put little bygons in those spots. And then there's exactly one on this side. And so this is the co-associativity axiom that you get for geminate comonoids. And you can take this and you can recover a pseudo comonoid, but you have to pick a delta L or a delta R to use everywhere, and you have to insert these isomorphisms. And that's a choice, and it is quite arbitrary which one you want to pick. And moreover, I would say it's a choice that forces you into a kind of unnatural stance in working through the rest of the theory. All right, that's all I wanted to say. So thank you very much for the invitation, and for everybody who's here in my office with me right now, or in Geneva, or watching later. I'll stop sharing that for a moment.
Thank you very much, Nick, for your talk. And unfortunately, we have no time for questions now, and we will resume in a couple of minutes with the next talk. Thank you again, Nick. We clap another round of applause for the speaker.
Thanks very much.
I apologize, Nick. We are just...
No, it's okay. It's okay.
And in a couple of minutes, we resume.